Early language models like Word2Vec had a strict limitation. They assigned a single fixed numerical vector to every word. This meant the word bank was computed identically, whether the text referred to a river or a loan. This brings us to algorithm 42 in our series, Transformers and Attention. Curious, how do we teach a machine that a word's meaning changes based on the specific words surrounding it? True machine comprehension requires a system capable of calculating the shifting relationships between every word in a sequence at once. In 2017, a team of researchers at Google Brain published a paper with a playful title borrowed from the Beatles, "Attention is All You Need." Their target was the industry standard, recurrent neural networks, or RNNs, which read sentences strictly from left to right, one word at a time. Time creates a strict bottleneck in RNNs. Data is forced through a fixed-size memory tunnel, where earlier words fade as the sentence grows. To solve this memory decay, researcher Jakob Uschgereit proposed a radical solution, throwing out the sequential left-to-right reading entirely. This highlights the architectural shift. RNNs are bound by O of n steps. The transformer computes every relationship in O of 1 parallel operations. By breaking the left-to-right chain, it treats the sequence as a single data block, making every word available simultaneously. Looking at the original paper schematic, you can see the result. When the recurrent loops are stripped away, we get a modular stack of encoder and decoder blocks. This relies on self-attention, a mechanism allowing every word in a sequence to look at every other word simultaneously to determine relevance. Eliminating those left-to-right dependencies allowed researchers to distribute training across massive GPU clusters, scaling language models up to billions of parameters. Here is how it works. Because the sequence order is gone, the model must explicitly inject positional encoding into the token embeddings, giving each word a unique spatial coordinate. The input splits into 3 projections: queries, keys, and values. Dotting queries and keys builds a grid of raw relevance scores. Scaled and cast through a softmax function, these become probabilities. Multiplied against the values matrix, they produce a contextually updated output token. This slide traces a microexample with the book's actual matrices. We can see how the attention weights blend the values together, so a word like great now mathematically leans on transformers. The architecture runs this entire process in multiple parallel heads, allowing the model to capture different linguistic relationships, like syntax or long-range references, at the same time. This sequence of linear algebra is the mathematical equivalent of context. It takes the abstract relationships between words and converts them into precise, weighted influence. Tracing the path up this schematic shows us that self-attention is not a black box. It is a highly optimized stack of matrix operations. This continuous recalculation of context is what keeps a generated story about a cat returning to words like purring, instead of introducing barking. Even when scaled up to hundreds of billions of parameters, the core logic remains simple and parallel. The entire engine boils down to just a few lines of NumPy. Let's open the notebook and watch self-attention compute, line by line. Open the Jupyter Notebook for Chapter 11 of the 50 Algorithms repository, and you'll find this exact Python function, self-attention. It's about 3 lines of active math, but this specific code block is the engine running inside nearly every modern large language model. By stripping sequence processing down to 3 matrix multiplications and a single softmax calculation, let's break down exactly how it works. The first step generates the raw scores. By multiplying every query against every key, it builds an n by n grid, mapping out how strongly every single token relates to every other token in the sequence. Next, the softmax function takes those raw, unbounded numbers and forces them into a strict probability distribution. Notice the axis equals 1 parameter here. This ensures the normalization happens strictly horizontally, row by row. Because of that specific parameter, the attention weights for any individual token will always sum to exactly 100%. Finally, we hit the weighted sum. The function multiplies these newly minted probabilities by the value matrix. Those 3 steps guarantee that each row of the output is a dynamic, mathematically weighted blend of the entire surrounding sequence. This diagram charting the book's 3-token example proves the math in action. You can see the query, key, and value matrices loaded and ready. Calculating the dot products between those matrices generates the raw relevant scores for how the tokens interact. Once that data passes through the softmax, we get the alpha matrix. Look closely at row 2. It assigns exactly 79% of its attention directly to the second value vector, with a 10% sliver given to the tokens on either side. Multiply that by the values, and the final output matrix emerges. That second token retains its core identity, but it mathematically pulls in precise fractions of context from its neighbors. The book's teaching code is perfectly clear, but it's missing one piece used in production. Before the softmax, you have to divide the scores by the square root of the key dimension. Without this scaling factor, large dot products will blow up the numbers, completely destroying the softmax gradients during training. Add that single division step, and you have the exact mathematical operation driving models like GPT, BERT, and Claude today. And that hardware bottleneck is exactly the problem engineers have to solve when processing massive context windows. Artificial intelligence has expanded into nearly every digital surface we touch. Beneath that expanding canopy of tools, there is essentially one engine driving the growth: the transformer architecture. It is the mathematical foundation processing text for systems like GPT, BERT, Llama, and Claude. Its utility stretches well beyond chat interfaces. It powers real-time global machine translation and transcribes audio with high-fidelity speech recognition. It has even crossed into entirely different scientific domains. It decodes the complex biology of protein folding inside systems like AlphaFold, and it processes pixel data through vision transformers. Because the transformer is the undisputed default for modern multimodal AI, software developers cannot treat it as a black box. To build with it responsibly, you have to understand exactly what it costs computationally. Older language models, like recurrent neural networks, read a sentence one word at a time. This architecture map shows the core mechanic driving that connection: a standardized multi-head attention block. These identical blocks can be stacked endlessly to increase the model's capacity. Total sequence parallelization, zero signal loss over long distances, and modular scalability. Together, these traits allow engineers to take a basic text predictor and scale it up into a massive frontier model. But that scale requires an enormous amount of electricity, silicon, and cooling infrastructure. The hardware is forced to grind under an inescapable mathematical constraint. This complexity chart reveals the flaw in the self-attention layer. Time and memory scale at O of n squared, generating an n by n grid of attention scores. If you double the length of the text prompt, the computational memory cost quadruples. The architecture is also notoriously hungry for data. Training a transformer from scratch demands massive text corpora and weeks of uninterrupted GPU cluster time just to learn basic language structures. And because it ingests all the data simultaneously, the transformer makes a strict trade. It gives up compute and memory efficiency to achieve total sequence parallelization. The longer the document you feed it, the more punishing that trade becomes. In production today, you deploy a transformer when you absolutely need that long-range reasoning. It is the ideal architecture for coding assistants that must accurately generate line 900 while actively remembering variable definitions from line 10. It is necessary for robust machine translation, where the target output must perfectly align with the source text, even when the grammar and syntax shift entirely between languages. And it is highly effective in enterprise search engines, using attention-based encoders to instantly map a user's query against fast libraries of internal documents. However, you should not reach for a transformer simply because it is an industry buzzword. If you are building a strictly streaming system, an ultra-low latency application, or a tool that only processes tiny sequences of data, an older lightweight model like an RNN or a GRU is significantly cheaper, faster, and perfectly adequate. This diagram illustrates where transformers and attention fit into the broader computer science landscape. They sit right at the center of modern natural language processing and recommendation systems. This breakdown is adapted from 50 Algorithms Every Programmer Should Know by Imran Hamad, available on Amazon and Pact. Next time, we move one spot over to Algorithm 43, Collaborative Filtering, and explore the mathematical technique used to guess what a user will love before they even know they want it.